So our third and final story about interesting research at DIKU is Tuukka Ruotsalo, who is an associate professor here at DIKU with DIKU's machine learning section, which he joined in September last year. So happy 1-year anniversary with us, Tuukka. As part of the Finnish brain drain that we are orchestrating here at DIKU, he is also from Finland and spends part of his time still, I think, with the Finnish Academy of Sciences. So Tuukka develops cognitive models that combine machine learning and human-computer interaction using responses from our brain, using EEG and other things. He develops new types of machine learning methods that can learn user intentions and preferences by measuring human cognition. Traveling has been restricted due to Corona, so just the fact that we have Tuukka with us is awesome. So, Tuukka, we're happy to have you. Please welcome him and please enjoy his talk.
Thank you very much. I'm really delighted to be here. It's actually my first physical talk at DIKU, so let's see how it goes. All right, today we're going to talk about cognitive interfacing with data. Another way of putting the title could be, how can we connect the human brain with an artificial intelligence? So we're trying to measure cognitive reactions that people have, users of computing have, and feed that back to machine learning models that can then react automatically to these brain responses. So, for example, you could think of a digital environment where you see text images. In this example, images of two faces, and when you look at them, what happens in your brain is slightly different depending on which image you look at, and also, of course, depending on your intentions, what you might be doing with the computing machinery. So we react to everything we perceive in the digital and also, of course, in the physical world, and that can be measured from the brain. Now, what we want to do is to take these measurements, model them using machine learning, and also take the digital information that we encounter in digital environments, model that, build joint models that can then learn automatically our preferences, our intentions, our affect, and various things. Something that's important to understand here is that brain-computer interfacing, of course, has been there for a long time. There are examples from the early 90s already where people tried to control, for example, the cursor on the screen that you see on the upper example. But what we're doing is fundamentally different. So what people start to call this now is reactive or passive interfacing. So it means that in the upper example where you're controlling the cursor on the screen, you're really hard trying to move it, right? So you're imagining I'm moving my hand, I'm not physically moving it, but mentally really trying to command the machine. While in the lower part, you're just reacting. You're showing something and you're, okay, that's how it felt, and we're trying to register that. And this is by orders of magnitude more difficult. So I'm not actively trying to command the machine, but I'm just reacting as I would normally react to any information that I encounter. Okay, so how can we use this? For example, we can try to mine things like relevance, if information is important to us, how we feel, affect, and various other things such as whether I prefer some content or not, as we will see further. Much of the examples that you will see are in facial images for particular reasons that I can talk you later. We've also tried this with other types of stimulation or digital input, text, video, and so on. But I won't be going into the details in these here. So the first grand thing that we found out is that when you put a neural network, I'm not going to talk about the architecture here in detail, but when you put a neural network to look at these brain responses, well, you can actually see that from these passive natural reactions that we have, we can get out a graded response. Okay, so we can say I didn't pay attention to it at all, I liked it, or I liked it a lot, and we can validate that it actually is reflected in the brain responses that you see. That's something called ERP, a plot that is about 800 milliseconds after you see something, so after visual stimulation. And we can also single trial decode it. So single trial means that we show you just one example of brain responses, and the machine has to decide whether you liked it or not, in this case. And we get remarkably high performance on these passive tasks where we didn't give any instructions to people. They just reacted to information normally. What we can also do is to do collective intelligence. So this is something that got into news all over the world maybe a couple of months ago. So if we put these brain responses of different people, let's say we would have reactions from all of you towards some content, we can actually build a model that reflects to different opinions arising from this audience. And what we can do is we can build models that can then detect targets, for example, very, very accurately. So much more accurately than we've seen before. So for example, if I'm saying you, okay, you should look at people with dark hair, and you'll be doing an experiment like this, we would be registering your brain responses, feeding them into a model that can then learn the dynamics of responses of many people, and then putting these models together to actually do predictions of multiple people. So we can collect information from many people to correct for the extreme noise that we see in these individual signals. So you might have one user who is thinking about the holiday last week, and you're not registering much. But if you put many people together, then you start to see dramatic improvement. We can get over 90% accuracy, which is normally well out of reach with these systems. So you can see with one user on the left side, we get less than 0.7 accuracy, but when we put more people on the task, we actually approach over 90% accuracy. What we can also do is not just to classify, not just to see did you find this interesting or not, but actually connect these models with generative networks. So generative networks are these new networks that don't only classify, but they actually generate new information that didn't exist before. So we can put a generative network to learn a model of the world, in this case human faces, and then test it with users. Their brain responses are registered, and then the system can generate you in completely new faces that were not there before, that match what you liked. So this is approximately what it looks like. So we call it a neuroadaptive model because it adapts directly to your neural responses. So it basically, in this multidimensional space, it traverses this manifold, which is here 2D, and it tries to find a convergence point on a image that would fulfill your intention. Here we're doing it for trying to get rid of the smile. So you can see the face actually morphing, and the smile is fading away. So we start with smiling face, and then while we register brain responses, the machine starts to understand that the features that encode the smile are actually not preferred, and it can generate completely new faces that fade this smile away. And again, it works surprisingly well. So normally we get these classification tasks, the accuracy is something like 70%, so 7 out of 10 we get right. But here, when we actually do the generative modeling and generate completely new information, we get again well over 90% accuracy when people actually pick the images that were generated, whether they matched what they actually wanted. We also did this for subjective tasks. So this is for attractiveness, whether you find no instructions at all what to do. You just look the faces, and we can reveal which faces you like and which you don't. And then we put them into this generative model to generate a completely new face for you that you should be finding attractive. And this is what it looks like. So again, it starts to converge to a certain face that you find. What's the nice thing that everybody laughs when we show this? It's guaranteed. Okay, there's another one, and now you can see it transforming to male because of the preference, and we get a little smile as well, right? It's nice. And we're running it maybe a little too long because the face actually converges much faster. And again here, the generated faces that we see, they match 90% accuracy. So when we show people random process faces and samples from the network, they actually 90% of the cases they pick the one that was generated for them. Okay. So a little bit of take home before I stop. So we have a new computing paradigm which actually can connect the brain responses of humans to machine learning models directly. So learn from human reactions to parameterize and actually even learn new models that take their input not from labels or other supervision signals, but actually directly from the brain. And we can do various things. We can do classification, of course, which is the classic thing, but also collective intelligence, generative modeling, and hopefully in the future new things that allow computers to actually negotiate with artificial intelligence. With that, thanks for your attention, and I'm guessing that the questions will be in the bucket.